Okay, so I've been waiting for people to show, but I don't see anybody on the live stream, and I don't see anybody on Zoom. I see two people on Zoom, and I see three people watching the live stream. And we can keep going, but this really isn't a very efficient use of my time then. If I have to do a live stream with just two people watching, then we might as well just do it on Zoom. Um, but anyway, um, let's keep going. But then if the numbers are going to stay this way the whole of this hour, then we won't do any more live streams because it really isn't a good use of my time to spend 3 hours a week if there's only three people on the live stream. Anyway, so let's work on this today since we are here, and we'll solve a couple of harder problems than we looked at last time. Last time we looked at a simple structure based demo, the data structure to store ESC101 marks and grades, and then we saw how we could convert it into a linked list so we could store multiple nodes. Each node would have the data for one student. So I showed you how to work with a linked list to begin with. Now let's work on this problem, and we'll spend a little bit of time on this because it's a very intuitive problem to understand. But what I'll do is I will show you how to use a whole lot of functions. So we'll have a very small main function, and all the work we will put in as many functions as possible, and that will give us also a good handle on how to use functions that include reading and writing to linked lists. So let's keep the code. Actually, we don't really need to see this anymore. Let's close this, and medium1.c is our file. And what are we aiming to do? We want some code that will shift all the entries in a linked list in places to the right, rotating back around the right edge. And as I said, I want to make this as modular as possible. So we can begin, and let's say, okay, let's put the boilerplate in, and then we'll talk about what we will actually do. So that's the boilerplate complete. Now what is the data? The data is just integers. So what do we need? We need type def struct, what do we call this? Let's just call it node. It's typical. And we will say int data. We will store the data here, and we will say struct node star next. This is the self-referential definition that is needed to form the basic unit of a linked list, and what we call this structure, we'll call it node. So now we have a data structure of type node that will store this integer valued data, and it will store the memory of the next entry of type node. What else will we need? So because we're going to be doing this with functions, let's figure out what functions we are going to use, and let's make those functions. First of all, we want to be able to print stuff. So we'll have a function of type node star. I am putting a semicolon because I'm defining the prototype, not defining the function itself right now. Similarly, we will require a function to input data, and what do we do with it? We can say void input data. Now, we did not talk about this before because I showed you code where the nodes were a fixed number. I was just using 3 nodes, and so I just defined them. I hard coded them. But it's also you can also come across a situation where you may want to create a node dynamically within your program. So let's use the function to do that. And what will this function look like? Well, it's going to return a pointer. It's going to return a pointer to an address that is storing a node data type. So it's going to have a return type node star, and well, here we're passing how many to create, I'm guessing, so we'll say int. Actually, we'll say int. In fact, we can we'll cross that bridge when we come to it. So these are 3 functions that we will need for sure, and now let's create these functions one by one. Actually, let's put these in order that we'll be using them logically. So what will I do now? I will make the function create node. And this is going to take an integer as input. So what will it do? It's going to put, let's say, x. So it's going to put this integer inside that node. That's what it's going to do. So let's, how will we do this? We'll say node star n equals, what are we going to do? We're going to malloc this. Malloc size of node, typecast to an address of type node. And now what do we do with this node that we have just created? We'll set the, so remember that this n is a memory address, so the data field should be set to x, and the next field should be set to null, because this is we're adding this to the end of the list essentially. And now this is going to return this address. So this is how we can create a new node in the linked list. And then how will we attach this to the linked list? We'll see. That we will see in the main function. Now let's see how to take inputs. So in this case, because we have a linked list where we care about things being placed back at the top of the list, so both the top and the bottom, which is conventionally called head and tail of the list, both of them are meaningful. So what will we do when we say we want to take some inputs? Actually, for that reason, we should not use a void type here. We should use a node star type. We'll return the address. And in that case, this is not going to take any entries. So so let me show you how this is going to work now. Node star input. So we are going to define 3 node addresses. Head, we'll set it to null to begin with. Tail, we'll set it to null to begin with. And we'll say some data point. Let's not assign it some value. And now we'll take inputs from the standard input. So we'll say while 1 scanf so we'll take this as an input, and what is the termination condition? We'll say if num is entered as -1, what do? We break. We return the head of the list. Otherwise, we say create a node and store this number num in that node. So what is this going to do? So actually, do I have this in the right order? I do have this in the right order. What is this going to do? Now head starts with null, and so if the first entry I make is -1, then what is returned is null. It means I had an empty list. So that's no good, and there's no use having an empty list. So what will happen is that if I enter some numbers, then it's going to keep scanning. So first time it scans, it says, let's say the number is 2. So now this condition doesn't apply, so it will say pt, this node star pointer pt is going to point to something which is going to contain num, which is 2, and which is going to point to null. So pt, the data field that is stored in the node that is stored at the address that pt is pointing to, is now going to read 2, and the next field is going to read null. Now if we say if head equals null, so if there's no head of the list so far, what do we say? We set this pointer to be the head of the list. So the address of this value, this location, is the address of the head of the list if it was not set before. And in fact, what we need to say is that not only is this the head of the list, the tail is also this, because head is going to be set on the very first instance. Then we also have to have an else condition. What happens if the head is already set? Then we will say the tail has to be changed. The end of the list should be set to that. So what does this do? So remember that we are working entirely in address space right now. We started this, so this function is, all it's doing is it is taking inputs for the linked list from the standard input buffer. So I start with setting head and tail as null. And what do I do then? Then I run this while loop. And the while loop is going to keep running until I enter -1. And what it's doing is, if the head is not set, or if the head of the list, if the first entry in the list is, the address is not set, I set that to be the address of the first point that was created. For all subsequent points, what I'm doing is this data structure that I have made, the tail, the next field in this tail pointer is going to be set to the address of the current point. And then what do I do? I also set tail to point to this pointer. So let's think about this. The first time I go through this loop, so the first entry I make, then this condition is satisfied. Head is null. So now head is changed to point to PT. And PT is what? PT is the memory address that this statement has assigned to the first entry in my list. Now when I do the second scan and it's not -1, now a new PT is created. So this function is called again, or this line is called again, malloc is called again, and it assigns some other address to the to store the second number that was entered. Now at this point, the head is not set to null. The head is set to the old PT, the value that was stored, or the memory address that was stored in PT the first time. So now head is no longer null, so this condition will not apply. And the tail of the list was also set to that first block. So the list had just one entry. So the head and the tail had the same ID, or they had the same address. When I add a second element into the list, what should happen? The tail of the list should point to the second element. Yeah. The head should continue to point to the first element. The head should not be changed. The tail should point to the second element. And what should the next field of the second element point to? It should point to the address stored in the second value, or in the second address. So remember that this tail right now is a pointer that is pointing to the first address. So when I say tail next, what I'm saying is the pointer that is stored in this location, which is the location of the first entry, the next field in that block should be set to the current PT value, which is the address of the second block. So the pointer of the first block should be set to the address of the second block. That is what this line accomplishes. And then the tail of the list itself should be set to the second. And now what will happen when we do this the third time? So again, this is not satisfied. This is going to create a third PT, a third address. Now again, head is not null, so we skip this. And now, what is the value that is stored in tail? The pointer to the second address. So the second address, the block that is stored in the second address, the next field of that block is now set to the third PT, the address of the third entry, and we set the tail to be the address of the third node block as well. So you can see that this will keep going. You keep adding entries. The previous entry's pointer is going to be the next field of the previous entry is going to be set to the address of the new entry, and the tail is just going to keep getting reset to the most recent entry. So this way we can, within a function, dynamically construct a linked list of arbitrary length. You can just keep making this. So how did we do this? We did this with this function that creates a node on demand and stores some data in it, and with this function which runs a while loop terminated by some condition. And with this combination we are able to construct a list with an arbitrary number of inputs. And then what will we extract out of this? So we've made this function. What's the one thing that we still haven't done? Where is this one? Okay. Now what will this return? It will return the head of the list, which will be a pointer of type node. This works exactly right. Okay, so when I showed you the demo last time, again just to make sure that everybody understands what's going on, in the previous code that I showed you on Monday, I was painstakingly setting up each of these pointers in the main function. So if I needed 3, I had to write all of this code, and for each one I was calling this input data function separately. Now in this new approach that I'm using, what do I need to do? I will say node star head, and I'll just say head equals input data, and that's basically it. That's all I need to start to essentially construct a linked list that has 3 entries, that has 7 entries, that has 50 entries. It doesn't matter. As many inputs I give in the scan buffer, that many inputs will be stored in this linked list that is being constructed using a combination of these two functions. So this is something that's sort of new. We hadn't looked at this before. I'm showing this to you now. Okay, so that's as far as the data entry is concerned, and we also want to be able to print stuff out. So the print is a straightforward function. We've already seen it before. Let's just write it, and then we will actually get into the basics of the code. So for print, we don't really actually need a return. We'll say print list, and this is going to take the head of the list as a parameter. So what do we say? We say node star ptr some pointer equals head, and then if head equals null, that's just the exception handling condition. If the list is empty, we just return. Otherwise, we say while the pointer is not equal to null, print this and keep the pointer moving along like this. Oops. So this function we've seen before, at least a version of this we've seen before. And now let me make sure that I haven't made a mistake. So what I'm going to do is I'm going to print out I'm going to take inputs and then I'm going to print them out just to make sure that I haven't done anything wrong. Print f the list contains the following values. I'm making a mistake somewhere. Oh, syntax error. Yeah. Yeah, I caught it. Okay, so now this, again, that's why I'm sort of running this now before we actually get around to solving the rest of it. What did I set it as? Oh, void print data. Okay. Now. Okay. Include stdlib. Okay. Oh, it compiled. Oh, I'm on the Windows machine. Okay, and now let's test it. Let's say 2, 4, 1, 4, minus 1. Okay, so I have a linked list and it contains the following values 2, 4, 1, 4. That is exactly what I wanted. Let's add some more. 45, 34, 76, 32, minus 12, 0, 32, 98, minus 1, 34, 23. You can see that all the values up until the minus 1 are stored in a linked list. So we have handled the input output of this question, and now what are we going to do? We have to rotate the list. So what that means is that we'll take an input. That input will be an integer. If the integer is 2, then we'll take the 1 4 in this 2 4 1 4 and we'll stick it here at the left, and the 2 4 will shift. So everything will shift by 2, and whatever is spilling over is going to go and be attached at the left. So even if you try to do this with arrays, this would not be easy. You'd essentially have to have a copy of the array and work with that. I mean, with arrays, what you do is you just say have a copy of the array and store the third to the end from the beginning, and then you would just take the first couple and stick them at the end. With the linked list, you can't do that. I'll show you one way to do it. Maybe you will find other ways of doing it. So let's begin. So because I've defined all these functions with prototypes, I'll define this one as prototype with prototypes also. How will we solve it? So let's node star, we'll say rotate, and what will this take as inputs? It will take a node pointer to the head of the list as an input, and it will take an integer, which is by how much is the list going to be rotated. Now in this we have to handle the base case, which is when the list is empty. So if head equals null, then there's nothing to do. You just return null. Otherwise, what can you do? So actually, you know what? There's a let's just take this through. So let's begin by defining some indices that we are going to need. Int count equals 0. I'll show you why I need these in just a second. And what else do we need? We need a node star start, and this essentially is going to be set to the head of the list, and we'll need a similar node star end, and we'll need a node star next. These are the three node pointers that we are going to need. Let me just skip this, pull this part below. So what this will do is, actually I shouldn't do this, I should keep this here. So if the head is null, then I'm just going to return null. Otherwise I will say while start, and this is going to be true whenever head is not null. So while start, I'm just going to say count plus plus, and I'm going to set end to be the same as start, and I'm going to say start equals start. next. So what am I doing? I have taken the start I have set to the head of the list, and then I have essentially run through the entire list. So whenever you see notation that looks like this is just a way of iterating through the whole list. I don't know where the end of the list is. I passed the head of the list, and in principle I could have passed the end of the list, but that makes things clunky. So because return function can only return one value, so I can't return both the head and the end. So I'm passing in the head, and so I'm storing that in this start pointer, and I'm saying while this is not null, that condition is already handled sort of here, I keep going, count plus plus, I set the end to start, and then I keep setting start to be whatever was in the next field of the node data type stored at the current start address. So the address that is stored in next for the first value is the address of the second location, and then in third and fourth and so on, and in the last entry of the list next is null, right? So remember that the tail is set to null, and so when we set the first value in the list, we set the head to PT and we set the tail to PT. We didn't do anything to the next. The tail next was always set to the PT value once the function reached this part. But whenever, so let's say that the last entry was made, and in that this command was not executed, so the tail is not set to anything, it's going to point to null. And so the next is not set to anything either, and so it's going to point to null. And when that happens, then start is going to become null, and the while loop is going to break. So by this process, I have accomplished two things. I have identified how many entries there are in my list, and I have identified the memory address of the last element of the list. I have accomplished both these things using this while loop. Now what do I do as I go further? So I'm going to handle the condition where the number of, or the amount of rotation is greater than the size of the list. So I say if n is greater than count, what do I do? N should be equal to n modulus count, right? So because I'm doing rotation, if I have a list that is 5 entries long and I say rotate it 13 times, that's the same as saying, or rotate it by 13, that's the same as rotating it by 3, because the other 10 times they'll leave the list unchanged after every fifth move. So the modulus function is appropriate. And now with this handled, if n equals count, or if n equals 0, in both those conditions, what do we say? We return the head, because the list is essentially not rotated. If you rotate it by its size, then you're not really rotating it at all. And now with these two conditions handled, we can work with the one non-trivial condition, which is we are rotating it by some number which is smaller than the count. So how will we work with this? We'll say count minus equals n, and we'll say the start equals head, and we'll say while I is not equal to count and start is a valid address, what will we do? We'll say I plus plus, and we'll say start equals start pointing to next. Again, we're just sort of iterating through the list. So what are we doing here? Let's say that the number of rotations is 2, and let's say count is 5. So my list contains 5 entries, and they have to be rotated by 2 to the right. So what I'm doing is I'm setting this count now to 3 instead of what it was before, which is 5. And now I'm starting from the head of the list, and I'm going up to the third entry of the list. So essentially I'm going to shift the head of the list from the 0th entry to the third entry, because that's where the action has to begin. Now what action are we talking about? We'll see based on this other pointer that I had defined before. Next equals start next. So what does this do? Remember that if I am rotating by 2, then the third entry in the list to begin with is now the last entry, or it should be the last entry once the rotation has happened. So what I say is I take the next value, which is the address that was stored in the third entry before. The third entry before was pointing to the fourth entry. So the address of the fourth entry is now stored in next. And what should the last entry of the list point to? It should point to null. So I took this list, and I took the third entry in this list, and I took the next field of this list, and I stored it in this temporary pointer, and I set its value, the original location's value, to null, because it's meant to be the end of the list. And then remember that I had taken the end of the original list. That address I had stored in this variable using this while loop. So now what do I do with the next field of this? I will set it to the head of the list. So I'm taking the next field of the fifth entry, and I am saying you point to the first entry. So I have tailored the first entry. I have stitched the first entry to the back of the list. And now, what is the last step? So look at the steps that I have undergone. Up to this point, I had changed nothing in the list. In this whole function that we started writing here, nothing had changed in the actual list. Everything was just handling edge cases and setting up the indices, the addresses, setting up the start and entries. The only changes we are making to the list are in these lines. And what are the changes? We are taking the fourth entry. We're taking the third entry and we are setting its next field to null. So we are saying you are now the last entry in the list. We are taking what was originally the last entry and we are saying the next thing that you're going to point to is what was originally the first entry. So 2, 4, 1, 3, 5 were the 5 entries. We said we will rotate this list by 2. So what I'm saying is, what we have inside is 2 is pointing to 4. Right now what is under the hood happening in the linked list is this is what is happening. This is pointing to null. So what I'm doing is I'm saying you, this guy, you should point to null. So with this line of code, what I have accomplished is actually the head of the list is pointing to the first entry, right? Actually, we don't need to write that. So now this guy is pointing to null, which means the link between 1 and 3 is now broken. But 3 is still pointing to 5. And what else do we have? We have 3 is pointing to 5. And then with this line of code, what we did is we pointed this guy here to the head of the list. So we pointed this guy to the head of the list. Originally we had the head pointing to this. Now we also have this pointing to this, and we have head pointing to this. So what is left? We say this. So we replace the, so what is this? We, at the point when we wrote this line, next equals start pointing to next, the list had not been touched. So next equals start dash next. So the next pointer is storing the address where this is stored. And so we are saying we make that, or we make head point to that. And so this is what we get. We get a new list that looks like this with these 3 lines of code. And that's it. We return the head of this new list. Hopefully that is sensible. I'm actually going to comment this because this is a useful thing for you guys to read when you actually read the code. But this is it. This is what I needed. This is my implementation of a rotation of the list. Now what I still need is what is the, this is, I just need to write the prototype of this up top. Rotate, this is just a prototype. And hopefully this will compile. Yep. And hopefully this will work. So I will say 1, 2, 3, 4, 5. Oh, it can't work because I haven't called it from the main function yet. So I have to call this from the main function. And let's get rid of this. Actually, we don't get rid of this. All we say is int m, let's just say m, print, please enter how much the list is to be rotated. Scan d result m, and now I'm going to print a list. That's what I'm going to do. Okay, so now this is my code, and let's run it, and I'm hoping it's going to work. So 1, 2, 3, 4, 5. Oh, -1. Let's say 2. And you can see that it works. So it was rotated to the right, and 4 and 5 were surgically attached up top. This is beautiful. This is exactly where the linked list paradigm becomes valuable. See how easy it was, and of course the logic had to be thought through, but then once the operations begin, it's very, very elegant. It's very, very straightforward. Okay, so I guess that's all we have time for today. But that's okay. I didn't plan to go quick. You have to speak louder. This is the condition where, well, you don't have to. That's if even if you comment this out, you would actually not compromise on the functionality. It's a question of computational efficiency. If you have this, then for this special case, none of these computations will have to be run. Yeah, you will directly return the answer. Yeah. Yeah. So that's, I mean, if you reversed these, if you put this below, then you wouldn't have to check for the n equals 0 condition. So essentially, because I have this modulus operation above, and then I'm doing this check here, I have to have this n equals 0 check. Otherwise, if I had it this way, I could just do this. I would not have to check for n equals 0 because that condition is already handled by this. It's because I have in my code I had the modulus above, and then that would turn to 0 for the case where n equals count, that I had that extra check. This is going to work also. Okay, so that's a miracle. We finally had a question on Zoom. Very good. Okay, so we'll stop, and on Friday we'll do some more linked lists, and we'll pick an even harder problem. We'll pick this one, and we'll work with it. So those of you who want can practice and come with your solution, and then you'll be ahead of the class. Okay, so let's stop for today, and we'll pick this up on Friday.